Hey there! Welcome to the first lecture of Fundamentals of Electric and Computer Engineering. So this lecture is going to focus on kind of how we talk about electricity, where it comes from, and how we use it in terms of engineering. So first of all, let's start with talking about electricity. We in language talk about electricity as, oh, it's the thing in the walls. There's something in the walls, goes through the wires, turns on the lights when you hit the switch. And that's a thing that happens, but it's not the most accurate way to think about electricity. Electricity is not a thing you can hold. It's more like a phenomenon. It's a property of matter. So if we take apart the word electricity, first of all, let's look at the word vanity. Right? Vanity is a similar word. Vanity is someone with vain tendencies, right? And vain is like being prideful, basically. Someone who's chronically about their appearance and stuff like that. Well, so electricity, then, if we take that same approach, electricity must be something with elect tendencies. Okay. Great. So something about the cascade of letters elect implies electricity. Let's figure that out. So we know what electricity does, right? In a toaster, electricity converts to heat, right? Or, it converts bread to toast. And a light bulb converts electricity from this battery, converts it to light, right? And light is, particles, photons. Photons are the particle that carries light, but they also behave like a wave. It's cool stuff, but it's not super related yet. Then there's, like, this microphone. This microphone turns sound waves into something, right? It turns it into what we call a digital signal. And you can plug it into, like, an amplifier and get big sound, right? Because it's converted what's out here in the physical world, an analog sound, the sound of your voice, into electricity, right? And then that electricity made sound again when plugged into this amplifier. So we know what electricity kind of does at an instinctive level, because everyone, at least in modern times, has grown up since birth with electricity. At least, in this country, for sure. So electricity powers devices, right? And there's something else about that too, which is this word powers. This word powers is also something that we speak about in language, but has a specific definition in science. So colloquially, powers, to power something is to turn it on, to give it juice, to make it go. And honestly, in science, it's pretty much the same thing. It's the amount of energy that it takes to make something do something. So electricity has a relationship to devices through power, and that's something else that just, keep in the back of your mind. It'll come in handy later. It is a mouse good tool for later, right? Well, so electricity enables our modern world, And I want to challenge you right now to try and write out what you think electricity is. We just talked about what it does. But pause the video, take you a few minutes, and try and describe what electricity is. What do you think it is? Where do you think it comes from? And keep that in your notes. So, once you're back from your pause and you're making your notes, let's look at my definition of electricity. And this is the most succinct definition I've managed to come up with. So, electricity is the ability of matter to transfer electric charge through its molecular structure. And zoinks, that is not a great definition. That definition, though accurate, makes brain go burr. So let's break that apart, okay? An ability of matter, that means it's a material property, okay? Material property. So this is a property of all matter, actually, to transfer electric charges. All right, well, electric charges, that's something we'll probably have to define further down, okay? So define below. We're going to define that one below. And then molecular structure, well, that one we probably have seen before. That is the material, right? That's how molecules are made of atoms. And how all of that makes matter, right? There's like billions of atoms in the tip of a pin, stuff like that. So this collection of words, this sure do be a statement. It actually has a meaning, and it's not that complicated. It's still kind of a rough definition. So let's keep breaking it apart and see if we can make it something even more intuitive, right? So let's look at electricity as a property of matter. So matter is made of molecules, right? We just said that. We just said that this is how atoms and molecules go together. So matter's made of molecules, and this is a piece of matter. It's something. It's a non-specific something for the purpose of our example. So just please bear with that. So this is a something. This is a sample of something, and it's made out of molecules. And these, you see how these are groupings of this really big green guy and this really little purple guy? Well, so that's a molecule. And each one of these orbs is an atom, okay? So molecules are made up of atoms. Oops. Let's use a reasonable color. Atoms. So each individual one of these things is an atom. And those atoms go together, right? Those atoms are some little purple guy bonded to some big green guy. And then those are all bonded together to make this chunk of some solid matter. So, these things are wee tiny little buggers. They are small. So we need something we need a way to model model this so that we can kind of visualize it, because it is really, really hard to work with something you can't imagine. So we created metaphors for ourselves, and that's what scientific models are for. And this one is called the Bohr model. It is named after some guy, Bohr, and he said, all right, y'all, I love your plum pudding model where you think all of those little subatomic particles are just there in some kind of goopy miasma. That's great, but this one's actually useful. We can actually learn some stuff about this. And so this has become the most this is the current accepted atomic model. It deals with energy. It's very cool. It tells us a lot of stuff with not a whole lot of symbols. So inside of an atom, well, first of all, atoms are the smallest. Atoms are the smallest unit of matter. Okay, so what that means is that you can break down a piece of graphite into atoms, and it's still graphite. But you cannot break it down any further, and it still be graphite, okay? So this is a silicon model. This Si is the atomic symbol for silicon. It's kind of a big deal in electronics. It's like our big semiconductor. We dream and maybe have nightmares in silicon. So silicon and every other atom has structures inside of it that make it up, and those are called subatomic. So those are subatomic particles. So this big round bit in the middle, we call that the nucleus. And the nucleus is made out of protons, which we represent with p to the positive, and neutrons, which we represent with n to the 0, or just n. What this means is that this particle, this p plus particle, is a positive subatomic particle. If you're looking at individual protons and neutrons, you are no longer looking at matter. Okay? Subatomic particles are no longer considered matter. So the other part, and the kind of the big part here that we care about in electricity, are the bits whirling around at bazillion miles an hour around the nucleus. That is not a scientifically accurate statement. These guys are called electrons, and they whirl around on specific energy levels. So all of these ranks, these circles around it, are called energy levels. We also call them shells. But basically, these are the only places you can find electrons, is here, 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 and so on. Some atoms have more or fewer levels, but they all have at least one, and they all have the potential to have at least one electron. So these guys are the electrons. And electrons are represented by e to the negative. Okay, so if protons are p to the positive, and we know they're positive subatomic particles, electrons are e to the negative, so they must be negative subatomic particles. And the ones that we especially care about are the ones on this outer ring. This outer ring is called the valence shell. And why we care about this is because when atoms go together to create molecules, it generally has to do with the valence shell. So atomic bonding, which is the process of atoms joining together to become molecules to become matter, atomic bonding involves the valence shell. And there are 3 types of bonding, and you should really look at a chemistry class for more details on that. All we really care about is that valence shell and the fact that when atoms bond, when atoms bond, their valence electrons start to interact. Bonded electrons interact. ACT, there we go. So, valence electrons and bonded electrons interact. So, when they do that, they start to move. And you can kind of see it here. This is not a super accurate drawing of bonding. Again, please, if you are interested in atomic bonding, consult a chemistry professor or chemistry textbook. But in the general sense, valence electrons, you can see, kind of whiz around this NASCAR track. So they start to move because there are positive and negative charges, right? So we said that the protons are positive in the nucleus, and the neutrons are non-charged, right? They're neutrally charged. So neutral or no charge plus a positive charge means positive. So the nuclei, the 2 nucleus, are positive, with these electrons whirling around being negative. So if we were to think about this like a bar magnet, we'd have the positive side and the negative side, and they create a field. They attract each other, and so you have an interaction, right? And that, if you were to say have a second magnet that was conveniently oriented to where the charges attract, this negative side would go to that positive side, and this negative side would go to that positive side, and that positive side wants to get to that negative side, and that positive side to that negative side. And so these 2 things wham together, right? They move, right? Well, so do electrons. Bonded electrons move because of charges. So, what exactly is charge, though? Right? We said that we'd talk about that a little bit later, and here we are. So charge is a property of subatomic particles. Is a property of subatomic particles. And subatomic, remember, means that it is inside the atom. It is below or less than or inside the atom. So the less than atomic particles, the atom being the whole thing, right? The subatomic particles have charge. Some of them are neutrally charged, some are positive, some are negative. Cool, right? So just like how atoms are the smallest unit of matter, and it's still being matter, right? There's a smallest unit of charge, and we call that the elementary charge. And we label it Q. This is a constant. And this constant is measured in coulombs. The value of this constant is 6.022 times 10 to the negative 19 in coulombs. And just as a future reference thing, I tend to write scientific notation like this. E minus 19 coulombs. This is the same. This is the same as this, right? This is just the way your calculator does it, and it can help keep really busy note pages and homework pages cleaner by just saying times 10 to the is equivalent to E and then the thing. Okay. I'm having a moment with this eraser. Okay. So this is a constant. So there's a general measure of charge, right? Because some things aren't going to be just Q, right? But we need to know about it. And so we represent that with capital Q to differentiate. But little q is our constant, and anytime you see little q from now on in electricity, it's gonna be this number. So electrons have a charge of minus q per electron. And that is important. That is one of the core facts of electrical engineering is electrons are minus q. All right, cool. So that was a lot. What the heck did we just read? That did not feel like electricity, right? That was chemistry. And I can't really disagree with you, but it was important. It was important chemistry. So let's do a little recap, right? So electrons have a negative charge. And we just said that charge is minus q. Just for accuracy. We also said that electrons allow atoms to bond together. All right. And the last thing we said is that electrons do this bonding. So electrons facilitate bonding. I'm going to embarrass myself by spelling that wrong. They facilitate bonding due to, I'll do in part, to their negative charge with respect to the positive nucleus. With respect to the pos nucleus. Okay, so those were the key takeaways here, right? Electrons, negative charge. Not a visible color. All right, let's try this one. Electrons, negative charge. It's probably not visible either. Last chance. Yeah, there we go. That'll do. All right, negative charge, right? And also, electrons bond atoms together, right? And they do this because of the negative and positive charges in the atoms. Okay, so what does this tell us? This comes down to the fact that since electrons move due to bonding, because remember we said that once they're bonded, they have this NASCAR track that they zoop around on, right? So since electrons move due to bonding, and since electrons have charge, it means that electrons transfer. They transfer charge through the molecular structure of matter. And, right, molecular structure is just the matter. It's the way the atoms go together, right? So electrons transfer charge. And how did I get to that thought? So electrons, right? Electrons have a charge. They have a charge that is minus Q, right? So they can be thought of as a charge, kind of. I mean, they, have a little bit of mass and is really not a very significant amount of mass. But they have a little bit of mass and they have this charge property. And they move, right? They're zipping around a nucleus, right? Or, their shared nuclei. They're moving. They are moving charges. And you can think about that as carrying it or transferring it. So sometimes you'll hear electrons called charge carrier. And so with all of that in mind, what actually is electricity? I think we can put it together now. So electricity is how easily electrons move. That's it. This big ugly definition up here, all it means is electrons move. That's it. That's electricity. That is electrical engineering. You got it. You won. That's all. So going back to our beginning little analogy, if vanity is to be of vain, then electricity is to be of electrons. That's what the elect means. Anytime you see elect in a word, electrons, electricity, electronic, it means there be electrons here. So with that kind of said, and to try and take a break from all of the conceptual big brain hurty, let's look back at how we talk about it in engineering, right? So Adam Savage is one of my personal heroes, but this quote is actually pretty accurate. The only difference between screwing around and science is writing it down. It's the scientific method, right? Well, the only difference, at least in my humble opinion, between science and engineering is what you plan to do with it after you write it down. Did you learn this to share it with the world, or did you need to build something tomorrow that does something with it? That is my experience with engineering, at least. So, how do we write it down, though? How do we write electronics down? We do it like this. We have symbols, and they honestly look a little arcane. And we do stuff. We do stuff to it. And this is a coded message. This is actually just a coded message. You could send a flower bouquet and it would probably mean something similar. It does tend to look maybe a little bit like magic, though. I mean, if you think about it, there's symbols, and there's lines that connect the symbols that supposedly make them do things. This one is totally not an anime reference. Nope. Yeah, so it is kind of anime alchemy, though, if you think about it. Because these symbols mean something. They tell us something. And at different points, we're getting values and numbers out of squiggles. Just squiggles. So let's kind of break down what those squiggles mean. So, we've got devices. And devices are anything? Just anything. No, not just anything. They're anything drawn on a wire. Anything drawn on a wire. So in this case, we're looking at this squiggly guy and these parallel lines and that set of mountains and these mountains and this circle, right? So those are all of our devices, at least in this circuit. There are other device symbols. I will draw a few of them. So things like this are sources. They can either provide current or voltage. This is also a source. It can do the same, either current or voltage. This is a source. This is a battery, and you might recognize that I drew up here in the battery, right? So that's also a source. That is specifically a voltage source. But again, we'll get into the details of that stuff later. You can have these mountainy things, and that's a resistor. And this bed spring is an inductor. And these hot irons, I guess, is a capacitor. And then you've got things like this, which is called a diode, and things like this, which looks suspiciously like a diode, but it is an amplifier. The this bar really matters. So what else? So there's wire, right? And that's the connecting lines. So that's the this stuff. This stuff and that and everything that brings all the stuff together. But it's also a few other things. And it is this. These are called terminals. And they terminate a wire. They indicate that a wire ends abruptly without connecting to anything. It'll be useful for later, I promise. This one is called a switch. And it might have one terminal it could connect to. It might have two terminals, and it might go up like this or down like this. Either way, this thing changes. This thing either opens the circuit or closes the circuit at a certain time. And then probably the most important thing of all is ground. You'll also see it GRD. We are consummately lazy. We have a lot of symbols. We already speak symbols, so we abbreviate stuff. I am sorry. But ground is probably the most important thing of all of these wires. Okay? Ground gives us a datum, and that word may or may not be familiar, but all it means is that it gives us a reference point. It is our reference point. Reference point. It's like saying 0 is the actual physical Earth on the y-axis. So 0 on y means you are at ground level. So same thing, except instead of height, we measure voltage in general. So for us, ground means 0 volts. And we'll get into the important values of a circuit in the next lecture, but so we'll discuss what voltage means later. For now, it's 0. It's 0 of the stuff that makes it go. Or the stuff that we care about that gives us some idea, some reference to what is happening. It is our reference point. It is our datum. So, because of this, you will hear it called the reference node. It took me embarrassingly long to put together that ground meant reference, or that reference node meant ground. I will save you that trouble. I will say it out loud. You will also hear it called ground node. And you might be asking me what a node is. A node commonly is just a point. It's just a point, or important connection in a circuit. Okay, so you may also hear ground line or reference line. So basically, in a circuit, we happen to have a circuit down here. In a circuit, you might see a ground attached somewhere. You might not. You might have to add it yourself. It's fine. We can do that. Whatever wire it is attached to is said grounded. It has been grounded. It is not allowed to go on YouTube for 2 weeks. It is grounded. But also, we call the line that it's on the ground line. Ground line. There. So ground gives us our reference point. Everything else is measured with respect to that. And we'll go into details with that a little bit later. But for now, let's go ahead and look at the rest of the anatomy of a circuit. So first of all, only complete loops are considered circuits. This is a circuit. So only complete loops are circuits. Right? So that's a loop. This one. Those are all loops. But this one's got terminals in the middle of it. It doesn't have a loop, right? It's got a hole here. We call that an open circuit. So disconnected loops are called open circuits. And nothing flows through them. Nothing happens. I mean, it can't. You have to have a complete loop to have a circuit. And this is a broken loop, so it's not a circuit. The next thing is picking out nodes. So we just said that a node is an important connection, right? Well, how do we know what's an important connection? Well, okay, so let's start looking at what connections are. Connections are where one device touches another device, or is otherwise wired into the circuit. So, like, for instance, this resistor is connected to the circuit here, right? And it's also connected here. This resistor is also connected here, but it's also connected here to this voltage source. So, how do we know which ones of these are important? Which ones of these do we think about as nodes? Well, so we look at places where 3 or more connections touch. So 3 or more devices connect. So we got one. Well, let's not just change color. We got 1, 2, 3, and 4. There's 4. So there's at least 3 here, right? How about this one? We got 1, no device here, no device here. Okay, well, maybe this one is not a node. Okay. What about here? We got 1 device, 2 devices. Okay, so that's less than 3. So this one, not a node that we care about. Also not a node that we care about. This one is a node. This one's also a node. It's important because it has 1, nope, 2, 3, yes, okay. How about this one? 1, 2, 3, nothing happening here. But it's still a node. How about this one? 1, 2, well, there's nothing happening here. Also, we know that this wire is effectively dead because this is an open circuit, so especially no. So this one, not an important node, not a node. This one's a node, this one's a node. So nodes are points where 3 or more devices connect to the same place. And this can be a little bit tricky because you can also draw it. You can draw things like this. Like that. So what's happening here? Well, okay, this is a blank wire. Well, empty wire between two points like this effectively doesn't matter. Effectively, you've just connected this point to this point with nothing happening in between. So they're the same point. These resistors are effectively drawn like this. That will help later, and we'll also reiterate some of this later on. So for now, though, in this specific circuit, an empty wire is called a short circuit. And it's called a short circuit because, actually, let me go back to using the right colors. It is a short circuit here because it's nothing happening. It's just connected this point with this point. Well, this point's not really doing anything. And also this point is connected to a short circuit to this point. So actually, in fact, this whole area here is the same point, okay? And it's all a short circuit. So this has connected to here, effectively. So short circuits connect devices directly. And you can also look at it like it's just any other segment of empty wire, but specifically short circuits can be a problem. Like say if you have a source of some sort and some device and then a short circuit here, well, electricity likes to take the path of least resistance, and I mean that pun intended. So it's gonna go through entirely this short circuit. This voltage source is gonna fry itself. It is going to die because it is just pouring its own voltage into itself. Nothing's happening here because this device automatically takes more energy for electricity to go through than this. It is, it's one of those funny things, but it is also a life hack that might help us out later. So that's all we got for today. I think that is, frankly, plenty and a lot of very, very conceptual stuff, but I believe that this will lay a strong groundwork. So next time we're going to look at circuit analysis, which is kind of what this class is predominantly about. It's how do I get data out of this mess of squiggles? And maybe even apply it. So in so doing, we're going to cover kind of the important values in a circuit and also the laws that really, really matter. Like the F equals MA of circuits, right? The thing that everything's built on. So that will be next time. All right. Have a good day. Please try and go decompress. Thanks for listening, and see you later.